There we go. What we are going to do today is we are going to end the day with titration. We're going to work into it by talking about solution concentrations, which we measure in what units? Molarities, and dilution processes. Along the way, you are going to learn an equation that is not on the AP cheat sheet that you do need to know. So now you're saying to yourself, I thought they all had to be on the equation sheet or they can't. Guys, the equation that you're going to be exposed to is actually a logical mathematical thought that they assume that you can come up with just because it makes sense. You'll see. Okay, so first of all, guys, there you have it. When we talk about solution concentrations, we are talking about molarity, which is our unit of solution concentration. Now, guys, molarity is defined as moles of... Oh, wait a second. I wonder if this is all going to be... No, it's okay. It's defined as moles of solute divided by liters of solution. Now, guys, understand that as we get deeper into the year, there are other units of concentration that we are going to talk about. There's one called molality, which is like molarity, only a little different. We'll get into those later. But for now, you just need to understand molarity is moles of solute per total liter of solution. We'll deal with that mathematically in a minute. What I want to do first is deal with it conceptually. Hi. You really can't. This is, could you come back at the end of class? Okay, that would be, sure, yeah. Okay, so guys, what we're going to do is we're going to deal with this conceptually, and we're also going to deal with it mathematically. So let's talk conceptually first. And guys, this ties back to the wonderful conversation that we had a few minutes ago about what happens when things dissolve in water. So here we go. When we express concentrations, we can do it one of two ways. We can talk about it in terms of the concentration of solute. This is what you are accustomed to. For example, you have 1 molar NaCl, or you've got 1 molar CaCl2. Both of those you know to be water-soluble salts, which means they completely dissociate. So you could make a 1 molar solution of NaCl, you could make a 1 molar solution of CaCl2. Now guys, again, this is what you're accustomed to. Here's the thing that you got to understand about these though. These two solutions, even though they have the same concentration, are not actually similar in concentration. You're going, wait a minute. They're both 1 molar. You just said they have the same concentration. So how are they not similar in concentration? Well guys, let me show you. You want to do this in your notes because you're going to be doing this on the test. Draw yourself a couple boxes. And in the top box, draw the species in solution for 1 molar NaCl. And in the bottom box, draw the species in solution for 1 molar CaCl2, calcium chloride. So what we're saying right now is these are both 1 molar solutions. They have the same concentration, but they actually don't have the same concentration. And hopefully after you draw the pictures, you'll understand why. So guys, this is the microscopic view of a beaker of table salt water. If you can look inside a beaker of table salt water, what are you going to see? Are you going to see any NaCl? No. You're going to see NAs and you're going to see Cls, right? So, you ready for the deep thought? In a solution of a 1 molar solution of NaCl, if you don't have any NaCl, this is actually not correct, right? There is no such thing as a 1 molar NaCl solution, because if you have a 1 molar NaCl solution, you ain't got any NaCl. So what do you actually have? Well, what is the concentration of Na? 1 molar. What is the concentration of chloride? 1 molar. So guys, this is actually a 2 molar solution of ions. It's 1 molar in Na, it's 1 molar in Cl, and it's 2 molar overall in ions. Now do you understand the difference? What do you have floating around in a calcium chloride solution? Do you have any calcium chloride? No. So what have you got? Well, you've got calcium ions and you've got chloride ions, right? But what's the relative ratio? 1 to 2. So guys, in a 1 molar calcium chloride solution, you ain't got any calcium chloride. So what's the concentration of calcium ion? 1 molar. What's the concentration of the chloride ion? 2 molar for a total solution concentration of 3 molar. Guys, this is the root of how they've changed AP chemistry this year. There are professors, chemistry ed professors all around the world right now. I actually met with one of them from Sydney, Australia. He's really a good teacher. And he would propose that we are crippling high school chemistry students by telling them there is such thing as a 1 molar NaCl solution. There is no such thing as a 1 molar NaCl solution. It doesn't exist. There's a 1 molar solution in Na and a 1 molar solution in Cl, but the very fact that we would write this down would say that we are crippling students because many of them actually believe that there's a 1 molar NaCl solution. My response to that was, general chemistry students don't understand enough to know that they don't understand. So I just tell them the stuff that's wrong anyway, because most of them don't even get it. And then I come back into AP chemistry and I try to clean up the mess, because you guys are actually the people that will take chemistry in college, who will eventually run into these professors, and then they'll come back and go, oh, at least Knappenberger's kids get it. Go ahead.
Is that true? That's true of all salts, right? It's not.
That's correct. So long as it's soluble, right? Absolutely. Yeah. I actually had a university professor come back to me a few days ago and say, from BYU, came back and said, thank you, because your kids are well prepared. Or it's actually a parent that knew that, was it one of your parents? No? Not that your parents are chem professors, but I had a parent during back to school night say, I'm the next door neighbor of a professor at BYU, and we were talking about you, and this professor wanted them to tell you thank you for him because your kids are actually really good at chemistry by the time they hit BYU. And my response to them was, I don't know who this person is, but if it's a university professor that takes the time to find out who their freshman chemistry students had in high school, that's amazing. Because most university professors hate their freshman students, and this guy actually takes the time to get to know them. So I was actually in awe. So, guys, you get the idea behind that? So basically, just a second, what we're saying is this, that this is also true. I wouldn't write this down because it's all over the board in blue, right? That's all of this. But guys, the idea is that these, when we talk about these solutions, we should actually talk about them in terms of particles. And when we talk about them in terms of particles, we all of a sudden understand that it's 1 molar in sodium, 1 molar in chloride, 1 molar in calcium, 2 molar in chloride. And that's actually what's in the solution. Go ahead.
So would it still work to say that you have like a 2 or 3 molar solution of alcohol or something because it's not separate?
Absolutely. And there's a name for that, Spencer. It's actually what's called the Van't Hoff factor. We'll talk about it when we talk about colligative properties. But the Van't Hoff factor is actually the number that tells you how many particles something breaks into. For this, it would be 2, and for this, it would be 3. For the non-electrolytes, it's 1. It means they don't break apart. Absolutely. You guys okay? All right. Here we go. So guys, not only can we talk about molarities conceptually and draw pictures, we can also use them as dimensional analysis conversions. So you tell me, here's an example of what I'm talking about. How many moles of solute particles are present in 2 liters of a 0.2 molar sodium hydroxide solution? Do you want to solve this, or can you just kind of look at it and go, okay, I get it? What if I do this really quickly? Here's the way this would work out. It says, how many moles of solute? So what we want to know is how many moles of NaOH. So our goal, and by the way, guys, you know that that's the abbreviation for mole, right? MOL. So we would simply go like this. 2 liters, 1 liter is 0.200 moles of NaOH, and we're done. Remember? So the idea here is that molarities we understand to be in the units moles per liter, and as such we can use it as a conversion between moles and volume for these solutions. And this is supposed to be a decimal and not a smudge. Yeah? Well, it depends on how it's written, because this just says moles of solute. It doesn't say moles of ion. The solute is NaOH. If it asks you for moles of ions, then you would double it. You guys good? All right. There you have it. Okay, so guys, now it's time to move into things that are new to you. Well, I guess that previous thought was new because that's stuff I don't share with general chemistry students, because they wouldn't understand it. This is not new. This is review. Guys, this is new. This you need to know how to do. All of a sudden I turned into Dr. Seuss. This is not new. This you should do. Right. Okay. So guys, you need to learn how to do dilutions. For those of you that are in the lab, you are going to be doing these for the rest of the year. For those of you that are not in the lab, you'll understand it conceptually and you'll get it from there. So guys, the bottom line is this. When we do dilutions, the thought is most of the chemicals that you use in lab, especially the acids. Do I want to do this? Yeah, all right. I hate this crap. I'll be right back. I really don't want to do this. I'm gonna. Okay. So guys, here's the way this goes. This stuff is death in a bottle. But unfortunately, and it's the worst part of my job, I have to play with this stuff a lot. So the idea is this, especially as it applies to acids. So we need acid in lab. Hydrochloric, sulfuric, nitric, acetic, all of these different acids. We need acids in lab. Now the problem is that this stuff is ridiculously expensive to ship. It costs 5 times more money to ship that than the actual cost of the, in this case, hydrochloric acid. So what do? Well, guys, it's similar logic to what they do at a restaurant. I got to take these off. I'm distant enough. A restaurant relative to Coke. Okay, you got the pop machine, and I think most of you understand this, that there's the big Coca-Cola truck, right, that drives around town delivering the Coca-Cola. But guys, if they're delivering to restaurants, they aren't actually taking cans of Coke to the restaurant, which they then pour in a hopper and dispense out of the machine, right? The way that they handle this is in the back of the restaurant. There are all these tubes that go back there from the Coke machine. And guys, in the back, there are these big old jars of concentrate. And then there's another jar of carbonated water. And when they buy the soda, they buy it as a concentrate, and then they dilute it in order to serve it. Why do they do that? It's cheaper. It's a lot cheaper to send you a 5-gallon bucket of concentrate and then let the restaurant dilute it than to deliver the hundreds of gallons of Coke that they go through in a day. Guys, the same thing is true of acids. It's a lot easier for me to buy this saturated at 12 molar than it is to buy the 0.01 molar hydrochloric acid that we need to use in lab. So what do you end up doing with the hydrochloric acid? You end up diluting it down from the stock bottles, which are saturated, down to the concentrations that you need. So this is concentrated hydrochloric acid. I've been teaching 23 years and I've had to order it once. That's how little of this you go through in a decade. That bottle, well, you can see, it's down to here, and that's been probably 10 years worth of use. Sulfuric acid saturates at 18 molar. That stuff scares the pants off of me. Guys, nitric acid saturates at about 14 molar, and so on and so forth. But what I have to be able to do then is I've got to be able to do some math and figure out if I don't want 12 molar, if I want 0.1 molar, how do I make it? That's the whole idea behind dilutions. So guys, I'm going to get this just out of the way. I'll just put it in here. I hate this stuff. Anyway, so guys, here's the way you do it. You do this using what is called a dilution ratio. And this is it. Molarity 1 times volume 1, or I'm sorry, not 1, we'll go with initial. Molarity initial times volume initial is equal to molarity final times volume final. So if you printed the notes, there's actually a question embedded in the notes. I'm not going to answer it. What I'd rather do is stick with the context of the bottle that I brought in here, and let's make up our own little thing. So guys, it goes like this. Say that we're getting ready for lab, and we need, 250 milliliters of 0.01 molar HCl. How do we make it? Now guys, let me tell you right now, you're going to see questions like this on the AP test. And when you see them, and it may not be this specific question, but you are going to see questions on the AP test that are laboratory questions. This would be a laboratory question. In lab, how would you make 250 milliliters of 0.01 molar HCl? This is a laboratory question. They will expect you to write procedures. We're going to talk about how to do that right now. So, do you understand the question? You're okay? Yeah. Well, yes. And so let's solve it and talk about it in context. So guys, the idea is this. To break the question down, the question is asking this. How much volume of the stock HCl, the initial scary stuff, what volume of that do we need in order to make a final molarity of 0.01 molar if we want 250 milliliters of it? Now, as you're saying, what information do we need to know in order to solve that? We need to know the molarity, and it's on the bottle. It's 12 molar. So what does the solution look like? Well, we would go 12 molar, again, you'd write down the equation first, but it's already there, 12 molar times X. So what volume of 12 molar do we need to make a 0.01 molar solution, and we want 250 milliliters of this stuff? And then we solve it. So we have 250 times 0.01. That, of course, is 2.5. Divide that by 12. And guys, the answer that I get to two significant digits is 0.21. Oops, let me draw that differently. 0.21 milliliters. Bless you. So guys, what does that mean? Well, here's what it means. This is a milliliter, right? So, in order to make, how much is 250 milliliters? What do you picture? Can of Coke. So it's about a cup. It's a can of Coke. It's a fourth of a liter. A liter is about a quart, four cups in a quart. It's about a cup. So in order to make a cup of 0.01 molar HCl, what's the pH of 0.01 molar HCl? 2. This is scary stuff. This will still mess you up. In order to make a cup of 0.01 molar HCl, how much of this stuff do we need? The answer is a fifth of this, right? This is a milliliter. 0.2 is a fifth of this. So you need that much. Get it? That's why this lasts a decade. You don't need that much to make still large quantities of strong acid. So, now let's turn this into the way you would need to write this in class. You ready? And this is going to become the running joke in the class. Let's just get it out there now. Guys, if you saw this on the test, the question would be this. Starting with a stock 12 molar solution, explain how you would make 250 milliliters of 0.01 molar HCl. You get the idea? Here's the answer. You want to write this stuff down in your notes. This is what they will demand of you on the test. Do you all understand that what we're doing right now is answering the question, how would you make this solution given the stock? They're asking for a lab procedure. Step number 1, put on goggles, apron, and gloves. If you don't write that down, they will mark the whole question wrong. And they need you to say goggle, apron, and gloves. You've never even used aprons or gloves, well, oven mitts, but that doesn't count. You've got to say put on goggles, aprons, and oven mitts, gloves. Every time you write a procedure, goggles, aprons, and gloves. Every time. Yeah. Yeah, you should have seen the uproar when they first started putting these questions on the test and they marked them wrong for students because they didn't write that, and then goes, kids should just understand that. No, that's a little nitpicky. It was a mess. Okay, so now guys, what are we going to do? How are we going to make this acid? There are some important things that you need to know. So it goes like this, and we've never talked about this before. For those of you that aren't in lab, I'd better go show you. I'll be right back. Guys, this is the magic that you have to mention by name. If you do not use the word volumetric flask, well done. If you do not mention the word volumetric flask, you will not get credit. So here's how you do it. Step number 2, get a volumetric flask. Actually, let's be more specific. Get a 250 milliliter volumetric flask. For those of you that aren't in lab, you probably don't know what this is. This is a 250 milliliter volumetric flask. This actually has a little line etched on the neck of it that measures 250 milliliters. That's all this thing can do, is measure 250 milliliters. Now, here's the place you've got to be really careful. From having done the math, you know that we need 0.21 milliliters of this, right? Now, this is an important principle. Eventually what we're going to do is we are going to take this acid and we are going to dilute it. So here's the thing you got to keep straight in your head. Do you add acid to water or water to acid? Guys, the answer is always acid into water. Now, let's talk about why. So what happens when acid and water come into contact? You'd better know this. What happens when acids and water come into contact? The acid attacks the water, right, and forms hydronium ion. That is and it's already happened inside the solution, but it continues to happen as you pour it into water as it dilutes. It's a very exothermic process. If you dump concentrated acid into water, it gets so hot it can boil. That's part of the reason I hate this so much. But guys, here's the trick. If this were to boil over, you'd rather have what is boiling over be mostly water rather than mostly acid. So the trick with it is this, and we'll turn it into a procedure in a minute. What you will do to dilute this acid, remember step 2 was get the flask. What you will do is you will mostly fill this flask with distilled water. Then what you will do is you will then add slowly the 0.21 milliliters of concentrated HCl. As that goes into the water, as heat is released, first of all, there's a lot of water there to soak up the heat. But still, if it boils, as it boils over, most of what is coming out is distilled water and not concentrated acid, and it's less dangerous. Does that make sense? So guys, always add acid to water. So let's turn this into a procedure. Are we on step 3? Partially fill the flask with distilled water. Then guys, step 4, carefully add 0.21 milliliters of concentrated HCl. Now what step are we on? 5. Step 5 would be swirl to mix. And then step 6 is add more distilled water to the 250 milliliter mark. Then step 7 is run as fast as you can and put the bottle of concentrated HCl back before someone dies. But you typically don't want to add step 7 to the test because they don't like that. But practically, it's really step 7. Step 6 is fill to the 250 milliliter mark. So guys, are you all okay? Got it? Okay, so those are dilutions, and you now know how to write procedures. It would be wise to know how to do that for the test. Now guys, finally this, titration problems. I am assuming that you can all hearken back, that's a good word, to the titration that we did at the end of lab, or at the end of the year last year. Remember we did it electronically? If you struggle with hearkening, it basically went like this. You had a burette. You had a burette and you had a beaker, and in the burette you had a base which you knew the concentration of. You had a volume of an acid that you did not know the concentration of, so you were trying to figure out the molarity of the acid by titrating. So what you did was you added base down into the acid until what happened? Well, it turned pink, right? But why did it turn pink? Because the indicator turned pink, but what is it that made the indicator turn pink? The pH reached 7, which means what? The acid was completely consumed by the base, which we call neutralization. And so the idea was that by carefully adding base to the acid until the point of neutralization, we could then use data from how much base it took to figure out the concentration of the acid. Remember that? Okay. So guys, you're going to see all sorts of funny little twists and changes on this theme. So, one of the things that makes AP Chemistry especially difficult is there's no longer steps, right? The 7 quick and easy steps to solving titration problems. These are not steps, because these are strategies. Because these problems are going to be all shades of different. But with that said, there are some commonalities that you're probably going to want to think about. And they go like this. When you're solving titration problems, you've always got to write a balanced equation. And unlike last year, they won't always balance with ones. Second of all, sounds a lot like dimensional analysis. Be careful to clearly identify your starting point and your goal. Then, guys, universally, when you're solving these problems, they will involve a mole-to-mole ratio from the balanced equation. And then, guys, finally, number 4, at times, you're going to have to make what I call external calculations to either fine-tune your starting point or fine-tune your goal to get exactly what it is you're looking for. Okay, so with all of that said, I've got at least one example problem maybe we could fiddle with. And then, guys, the remainder of the time will be yours to work on homework. We are doing pride today. So as you're writing this down, let me explain to you how pride is supposed to work, because a lot of you had teachers last year that just played with the system and didn't actually adhere to the way this is supposed to work. So guys, if you have a DF or an NC, after the bell rings at the end of 3rd period, you are no longer my student, you are my hostage. And you will not have access to me because you're no longer a student of mine. You are simply locked in my room because you have not earned pride. Now guys, understand that we do not have an hour-long lunch at Orem High School. We have a 35-minute lunch preceded by a 25-minute study period that if you don't need it, as demonstrated by you having good grades and attendance, you can use that to do whatever you'd like, include extend your lunch. But guys, we don't have an hour-long lunch here. So the way this works is that when the bell rings, I'll read off who is in here for pride. And again, guys, if you're on the list, you're here. You're not leaving. I don't care what teacher has wronged you because they haven't recorded an assignment that you turned in 11 weeks ago. Guys, you are here. I'm not going to let you go. I'm not going to let you talk to other teachers unless you have an eye. You're here. That's the way this program works. If you would like to talk with me during this time, if I don't have other people coming in for pride, then we could probably work something out. But understand, guys, that's the way this should work, regardless of experiences you had last year. So, you guys all caught up? Yeah.
So if you got an eye from you,
yeah. Oh yeah, then you're welcome to stay. Yeah, then absolutely. Yeah. So guys, the surefire way, if you want to talk to me during pride, is get an eye. Because I manage eyes very carefully so that I can focus on the people that have come to me and said, hey, I want time with you. That's not going to be today because I have some general chemistry kids coming in to have the safety talk. So I won't be available today. You guys done here? Okay. Let's give you a second to solve this. Then we'll solve it together. And then, guys, we'll give you some time for homework. These are apparently things indicating eligibility for National Honor Society. I would encourage you not to dwell on this. I just want to make sure I give these to you. I'm normally really bad at handing out stuff to students because, frankly, it has nothing to do with my world. But I think this is probably something you care about. So guys, if you're looking at this and going, I have no idea how to solve this, try writing a balanced equation. Huh. That's not yours, by the way. Good heavens, I'm getting dizzy. All right, I'm going to do the rest of these later. I need to re-engage. So guys, what about this? If you're stuck trying to write a balanced equation, maybe we could do that together to sort of prime the pump. So the question says this: how many grams of chloride ion are in a sample of water if 20.2 milliliters of 0.1 molar silver ion is required to react with the chloride in the sample? So guys, what we've got going on here is we've got some chloride ion floating around in water. We are titrating that with silver ion, and our product is going to be a silver chloride precipitate. So guys, how about if we have a little chat before you go into this any further? Maybe it would be helpful to visualize what's going on here. So we're titrating this stuff. So let's sort of talk about what this might look like. So there we've got our burette, and here we've got our beaker. And guys, let's figure out who's where. So what's in the beaker? Is that the chloride ion dissolved in water, or is that the silver ion? It would be the chloride ion, because we want to know how many grams of chloride ion are down in the water. That's the thing we're studying. So this would be the chloride ion down in the water. Now, what then is in the burette? The silver ion. But guys, here's the deal. You cannot just take your precious silver earrings, huck them in a burette, and make silver ion solution. Silver is not water soluble. It will sit there forever and not dissolve. So guys, how do you get silver ion into solution if silver doesn't dissolve? You need a salt of silver that will dissolve in water. Yeah? So what would be a logical choice if we need a soluble silver salt? Silver nitrate, because all nitrates are soluble. What about silver chloride? No. That's our product. What about silver acetate? That would work. But guys, silver nitrate would be our cheapest and most readily available choice. So what we've actually done is put silver nitrate, 0.1 molar silver nitrate solution in the burette. Now, why is it whoever wrote this problem didn't mention the nitrate? It's a spectator. It doesn't need to be there. But we as ever, growing chemists need to realize that there's no such thing as just silver ion solution. It was made from a salt that is supported by an anion, in this case, nitrate. You get the idea? So then the question is, if we took 20.2 milliliters of this, what mass? How many grams of chloride are down in the beaker? Okay? So again, let's clean this up. Here's our balanced equation. Excited to report my pen is working better. So now, guys, maybe you have a better shot at doing this. So if nothing else, you've got the information from the problem. So I'm going to steal this from you for a second. Is that okay? Okay. I'm realizing I forgot to print pride reports. And so I'm going to do that while you're finishing this up, just to be all like efficient and stuff. You guys all, of course, have pride today, right? Don't hurt yourself. Okay, guys, I'm got that done, and hopefully that was enough time. Why don't we solve this thing and see where you're at? So again, I didn't give you steps, but I gave you suggestions, but conveniently enough, the suggestions actually kind of guide the process. Suggestion 1, write a balanced equation. Suggestion 2 was, you'd better pick a starting point and a goal. So guys, it says how many grams of chloride, which would probably tell us we're solving for grams of chloride. Then, what information do we know that might lead us to an amount of chloride? Well, that would be the volume of our nitrate solution that was necessary to tie up all the chloride. So now let's start solving this thing. We're going to go milliliters to liters because that always feels like the right thing to do. But guys, that is liters of our silver solution. So now where can we go from there that would get us closer to a mass of chloride? Liters to moles, because 1 liter of this solution has 0.100 moles of silver ion. Now we're in moles of silver ion. Now guys, always when you're doing titration problems, there's going to be a mole to mole ratio. So the mole to mole ratio is 1 mole of silver ion to 1 mole of chloride ion. That's why we wrote the balanced equation. Now the last step's easy. A mole of chloride ion weighs 35.5 grams, and you can figure out the mass of the chloride. I don't think we need to do the math. You guys okay? Okay. So guys, with all of that said, oh no, all right. Here's your homework. 59, 64, 67, 75, 79, 85. Here, I'm going to stop recording.